Alright, here are quiz 8 solutions for Math 111. We're given some huge polynomial, a 7th degree polynomial, and asked to see if either of these two are a root. And it says one of them are. Okay, to test if something's a root, all we gotta do is plug it in to the polynomial. If we see an x, replace it with the 1. And if we get 0, it's a root. If we don't, it's not. So 1 to the 7th power is just 1. 1 to the 6th power is 1. 3 times 1 to the 5th power is 3. 5 times, we all write instead of talk. Question is, does this thing equal 0? Well, let's see. 1 plus 1 is 2, plus 3 is 5, minus 5. All right, we're back at 0. What about over here? Negative 16 and negative 16 is negative 32. Negative 32 and negative 48 is negative 80. Plus 80 looks like we're back at 0. So, I don't know what word that is. So 1 is a root of this polynomial. Yes. What about negative 1? Negative 1 to the 7th power is negative 1. Negative 1 to the 6th. 3 times negative 1 to the 5th. And so on. You'd end up with this mess. Does this thing equal 0? It doesn't. What does it equal? I don't care. It's not 0. How do I know it's not 0? Well, 80 and 48 and 16 are very, very positive. I only get to take away negative 3, negative 5, negative 1. There's not nearly enough to get it back down to 0. It's not 0, so no, it's not a root. This one is, this one's not. Good enough. Use polynomial Ling division. I guess that's supposed to be polynomial long division. To factor out the term corresponding to your root from part A. So we figured out 1 was a root. So what that means is x minus 1 must be a factor. X minus 1 is a factor. Then when I do polynomial long division, x minus 1 goes into x to the 7th plus x to the 6th plus 3x to the 5th. Wish I had left you more room in here. Minus 5x to the 4th. I wish I had chosen a smaller polynomial. At least it's the only problem on this quiz. Plus 80. Polynomial long division. I should get no remainder. Let's see if I get no remainder. To get rid of x to the 7th, I'd want an x to the 6th up here. Because x to the 6th times x minus 1 gives me x to the 7th minus x to the 6th. And now if I subtract, x to the 6th minus negative x to the 6th leaves me with 2x to the 6th. To get rid of 2x to the 6th, I need 2x to the 5th up here. Because that times x gives me the 2x to the 6th, and that times negative 1 gives me negative 2x to the 5th. Again, I subtract. 3 minus negative 2 is the same as 3 plus 2, 5x to the 5th. To get rid of 5x to the 5th, I need 5x to the 4th up here. 5x to the 4th times x gives me 5x to the 5th, times negative 1 gives me 5x to the 4th. So what I have is negative 5x to the 4th minus negative 5x to the 4th. I just left with 0. This column cancels out, and this column cancels out. That's good. So then this column, I'm left with negative 16x cubed and a negative 16x squared. To get rid of this negative 16x cubed, I'd need negative 16x squared up here. Negative 16x squared times x is negative 16x cubed. Negative 16x squared times negative 1 is positive 16x squared. Now if I subtract, negative 16 minus 16 is negative 32x squared. To get rid of this negative 32x squared, I need a negative 32x up here. Negative 32x times x is negative... What am I going to do here? All right, I'm going to recopy this up here. Negative 32x squared minus 48 and draw a little arrow. So when I do this negative 32x times x, I get negative 32x squared. Negative 32x times negative 1, I get positive 32. And now when I subtract, negative 48 minus 32 is negative 80. And I bring down this plus 80. These are all x's here. To get rid of this negative 80x, I'd need negative 80 here. Because negative 80 times x is negative 80x. Negative 80 times negative 1 is positive 80, and thank God I get no remainder, so I don't have to do that again. Use polynomial long division to factor out the term corresponding to your root. I'm fine if you leave it just like this. Whatever. Leave it like that. All right, I guess I shouldn't leave it like that. I'm fine if you leave it like that, but really what you want to do is recopy that thing. So this thing equals this guy. And maybe I'll even write just this is fine. So I don't really care if you follow the directions explicitly or if you just show this right here. Either way is fine. Anyways, what we're saying is this mess of a polynomial is really just this guy. And now we can factor this guy. Factor the remaining 6th degree polynomial, so that x to the 6th plus 2x to the 5th plus 5x to the 4th minus 16x squared minus 32x minus 80 by grouping. Factor the 6th degree polynomial by grouping into the product of a 4th degree polynomial and a 2nd degree polynomial. So use factoring by grouping. If you group these first 3 terms, they all have an x to the 4th in common. If you pull out that x to the 4th, you'd be left with x squared plus 2x plus 5. My goal is to be left with x squared plus 2x plus 5. If I want that to happen, I'd have to factor out a negative 16 over here. If I pull out a negative 16 from negative 16x squared, I'm left with just x squared. If you pull it out from negative 32, you're left with plus 2x. And negative 80 divided by negative 16 is just positive 5. And so what you get is that this 6th degree polynomial is just x squared plus 2x plus 5 times x to the 4th minus 16. Factor the 4th degree polynomial as a difference of squares. All right, x to the 4th minus 16 is a difference of squares, so it's just x squared minus 4 and x squared plus 4. If you want, you could go a step further. You could say x squared minus 4, maybe I should write it down here, is x minus 2 times x plus 2. But x squared plus 4 I can't take any further. Either of these are totally fine. I don't care which one you do. Solve for all 7 roots of the polynomial. All right, so now you kind of want to go back and figure out what the hell we found. We got an x minus 1 was one of the roots, or one of the factors. And then we had that times this whole thing. But this whole thing we figured out was this times this. It was x squared plus 2x plus 5 times this guy. Oh wait, but this guy was this times this. X squared minus 4. Actually, I'm going to use this form of it. X minus 2, x plus 2, x squared plus 4. Something like that. And so I want to find the roots. I set it equal to 0. It tells me that either x minus 1 equals 0, x squared plus 2x plus 5 equals 0, x minus 2 equals 0, x plus 2 equals 0, or x squared plus 4 equals 0. Solve this one, just add 1 to both sides. Solve this one, quadratic equation or complete the square. I'm going to complete the square. So I'm going to subtract 5 from both sides. Then I'm going to add 1 to both sides. Then I'm going to recognize that the left-hand side here is really just a perfect square. Then I'm going to isolate the x. So x plus 1 equals plus or minus the square root of negative 4. However, the square root of negative 4 is just 2i. So what I get is that x is equal to negative 1 plus or minus 2i. 2 roots down here. Solve for all 7 roots. There's 1, 2, 3. X minus 2 equals 0. That's easy. Just add 2 to both sides. There's 4. X plus 2 equals 0. Also easy. Subtract 2 from both sides. There's 5. Solve this guy. I only wrote the letter x one time, so I can solve it by isolating it. In other words, subtract 4 from both sides, then take the square root. Remember that if you take the square root, you got to put in the plus or minus. The square root of negative 4 is just 2i. So what I get is 2 more roots here. All 7 roots. 1, 2, 3, 4, 5, 6, 7. All right, I guess I'm good. Express this polynomial as a product of 7 linear terms. Fine. Once you have the root, it's easy enough to express it as a product of linear terms. If 1 is a root, x minus 1 is a factor. If this mess is a root, x minus this mess is a factor. If 2 is a root, x minus 2 is a factor. If negative 2 is a root, x plus 2 is a factor. If 2i is a root, x minus 2i is a factor. And finally, if negative 2i is a root, x plus 2i is a factor. Express this polynomial as a product of 7 linear terms. Here you go, 7 of them, they're all linear. That's finally the end of the quiz.